Hello and welcome to Brian's Biology. I'm big, bad, baldy, bearded Brian. I'm going to bombard you with biology, baby. So let's get right into it. Okay, so this channel is designed to help anybody undertaking any high school biology course. Particularly, we're going to be focusing on concepts common to AP College Board Biology and IB Biology. That's the International Baccalaureate Biology. But indeed, these concepts will apply to pretty much any high school level or even university level biology course. Okay, so we'll begin with Biochemistry 101. All right, a little foundational chemistry to begin with. So I hope that you enjoy. Biology is a story. In fact, it definitely is the greatest story that's ever been told, because it's a very real story. It encompasses all of our lives and all of the interactions that we have with our surroundings, and of course all the other organisms that we know to exist, at least on this earth. So, any great story needs to be told in an appropriate way. And if you look at the format of Hollywood movies or any other great storytellers, you will see they follow three main phases. 1, introduce the characters. 2, establish relationships. And 3, flesh out the story, make it a little bit more exciting. So today, we're going to do exactly those 3 steps. So who are the main characters of the story of life? Well, the answer is atoms. Okay? Not all atoms are as heavily involved, and we have a main cast of 4 atoms. That is carbon, hydrogen, oxygen, nitrogen.
CHON. Consider element X, a hypothetical element of course, but imagine the numbers A, B, and C in these relative positions. Now for element X, A is equal to the atomic number. This is the number of protons that the element has. B is the atomic mass number. This is the number of protons plus the number of neutrons. C is the charge. It's either plus or minus, and is the difference between the number of electrons and protons. So, A is the number of protons, B minus A is the number of neutrons, and A minus C is the number of electrons. Let's do some examples. Here we go. Calcium. Atomic number 20, atomic mass number 40 with a charge of 2 positive. This is our A, B, and C. Now let's use these formula to get the number of atomic particles. A, the number of protons, A is equal to 20 protons. B minus A, the number of neutrons, B minus A is 40 minus 20, which is 20 neutrons. A minus C is the number of electrons. A minus C is 20 minus plus 2, which is equal to 18 electrons. Now it's important that you take the charge into consideration here. Let's do another example that illustrates that even better. Chlorine, atomic number 17, atomic mass number 35, with the charge minus indicating 1 minus. Again, A is the number of protons, A is 17 protons. B minus A, the number of neutrons, B minus A is 35 minus 17, which is 18 neutrons. A minus C, the number of electrons, A minus C is 17 minus 1, which of course becomes plus 1, that's why it's important, 18 electrons. Now, pause the video, please don't cheat. You need to practice. Practice makes perfect. So please have a go at the following problems. Pause the video and list the number of protons, neutrons, and electrons. Rewind if you need to. I'm so glad you didn't cheat. Here's your reward. Hopefully you got them all right. If you did not, please rewind. Go back and have a look. See if you can use the formulas again to get the answers right. Practice makes perfect. But if you got them all correct, then congratulations. Let's move on to the next part of the lesson. So, of our 3 objectives, we have deciphered the number of atomic particles in atoms. Next, we're going to draw atoms given the number of atomic particles. Let's begin. Here's a hydrogen atom with 1 proton and 1 electron. The proton is arranged in the nucleus. Neutrons would also be arranged here, but because this hydrogen atom doesn't have any, we've only got 1 proton. Surrounding it is an orbital. Inside that orbital field, we have placed an electron, or at least what represents an electron. This electron is a single electron, a valent electron. Oxygen has 2 electrons in the first shell, but because it has a total of 8 electrons, it's able to fit 6 into its second shell. Now the second shell could hold up to a maximum of 8, so oxygen's 2 away from having a full complement in its n is equal to 2 second shell. Here's carbon. Carbon has 4 valent electrons, 2 electrons in the first shell, which are full. Always fill the first shell first, and the second shell containing 4. This is a very important valency, as it tells us an awful lot about carbon, which we'll see when we handle objective number 3. When filling in electron fields, always remember to fill in the first shell on the inside and work your way outwards. Here we see nitrogen with a full complement in the n is equal to 1 shell of 2, and 5 as its valent electrons in the n is equal to 2 shell. It has 5 electrons. Not a particularly significant number when it comes down to exciting properties that atoms might have. So, we can now draw atoms given the number of atomic particles. Okay, just remember to put neutrons and protons in the nucleus and electrons in the shells, filling the first inside shells first. The number of valent electrons is described as the valency.
Okay, so now it's time for objective number 3, predicting the properties of atoms based on their structure. Now, for this we're going to look particularly at something we just learned about, which is electrons going into shells. In particular, what we call the valent electrons, which give the valency of the atoms. This valency is going to help us to predict how these main players in our story, the atoms, are going to interact and form relationships with other atoms. Okay? So, valency. Number of electrons in the outer shell. How to think about that? Well, imagine that you had $999,999 in the bank. You're not quite a millionaire. You need $1 more. Wouldn't you be quite desperate to get that extra dollar? Well, what about if you had only $1 in the bank? You would need $999,999 in order to get to be a millionaire. But perhaps you wouldn't be so keen and so eager, given how far away you are from actually achieving that. So atoms behave in a similar way. An atom that's extremely close to having a full outer shell, maybe 1 electron away, is going to be very, very active. It's going to really want to engage with other atoms and either gain or lose that electron to have that full or empty outer shell. Hydrogen is a perfect example of this. Given it has only 1 electron, and that electron is in the first shell, where there's a maximum of 2, means it's 1 away from being full, and it's 1 away from being empty. This means that hydrogen is an extremely reactive atom. Why is that important to life? Well, we have a lot of reactions. Hydrogen is a very small atom, it can be moved around, and with a valency of 1, it's also highly reactive. And these are properties that really make hydrogen quite important. Not to mention, hydrogen is the most common atom in the universe. So for these 3 reasons, hydrogen is one of the main players in our story. What of carbon? Well, we call ourselves carbon-based life forms for a reason. There must be something special about carbon. And indeed, its special property also comes from its structure and its valency. It has a valency of 4. Now, you might think, okay, well, that's sort of like having $500,000 in the bank. You have $500,000 in the bank, you're as close to being broke as you are to being a millionaire. So carbon itself isn't particularly reactive, at least not compared to things with a valency of 1, like hydrogen. However, it is incredibly versatile in how it reacts. Carbon with a valency of 4 can either lose or gain 1, 2, 3, or 4 electrons. Okay? And that means it can react with a lot of other different atoms. I suppose if we're making the analogy of atoms having relationships, hydrogen is dying to have a relationship. Okay? But it can really only have relationships with things that are going to take or give 1 electron. Whereas carbon is very relaxed. It's very, very blasé about the whole thing. But it can react with many different kinds of atoms by either losing or gaining 1, 2, 3, or 4 electrons. This versatility is perfect in life because we're going to build macromolecules on carbon skeletons, and because we're able to interact with many other different types of atoms forming bonds, which we'll talk about in the next lesson. That makes carbon like a molecular glue. Not to mention that carbon being able to have bond with 4 electrons, or up to 4 electrons, it can also go in 4 different directions, meaning we can build big 3-dimensional molecules, which we'll see in later lessons. So, why use oxygen and nitrogen? Because they are available. If I sent you to a beach and I said build a wall, you would build a wall out of sand. If I sent you to a forest and told you to build a wall, it would probably be made of branches. And if I sent you to a quarry, as per stone is common, you would build a stone wall. Well, life on this planet uses oxygen and nitrogen because they are abundant. Oxygen, it might surprise you, wasn't particularly important to early life, and that may be something that evolved later on. Having said that, we can see that the structures of hydrogen and carbon and their valencies make them intrinsically important to life, and the structure of the atmosphere in which life evolved, being composed of oxygen and nitrogen, means that these 4 atoms are the big atoms in this story. Okay, so now I hope you enjoyed achieving our 3rd objective.